I'm Ben.
And I'm Oliver.
Welcome back to the Orange Podcast. Today we have a fascinating guest on our podcast. He's a trained medical doctor pursuing his passion in synthetic biology and artificial intelligence. His team has pioneered the world's first biohybrid computing platform, demonstrating they can teach human brain cells in a dish to play the video game Pong. This has gained, obviously, worldwide media attention. Welcome, Hon Weng Chong, founder and CEO of Cortical Labs. Thanks for coming.
Thanks for having me.
Lovely to have you on the podcast, Hon. So I suppose we'll start by just, getting a bit of an introduction about who you are and what you're working on.
Sure. So as you heard, my name is Hon Weng Chong. I'm the CEO and founder of Cortical Labs. Was actually a medical doctor before going on in a startup journey, and also a fellow alumni of Melbourne Uni. So it's always good to be back. They didn't have this Melbourne Connect building when I was training, and it's really cool to be in here and seeing all this cool facilities up and running. Let's see, where shall I start?
I suppose tell us maybe a bit about Cortical Labs. What do you actually do there?
Yes. Okay. What do I do there, or what does the company do? Those are two different things.
What does the company do? We'll start with that.
Okay. So Cortical Labs is a deep tech startup that was founded in 2019 with the goal of trying to build a biological computer. The inspiration for that really was the observation that there's a race to build AGI, artificial generalized intelligence, and the leader in the space back in 2018, 2019 was DeepMind. Using techniques such as reinforcement learning through demonstrations such as AlphaGo, where they trained an RL agent to defeat Lee Sedol. So that was the first time we solved the game of Go. Well, technically, we didn't really solve it, but we figured out a hack to actually make a computer play better than a human. And, OpenAI today, is the leader when it comes to the AGI space, particularly with the use of large language models such as ChatGPT. But our approach is slightly different. The way we've done it is by saying, look, the only truly generalized intelligence that we know of are biological in nature. Things like you and I, a dog or a cat or an octopus, have very, very interesting properties, such as the ability to model the world, to operate in it, avoid being prey, finding food of your predator, and so forth. The physical space and the operation in real time are actually really impressive feats of intelligence. And if you look at it, what do all these organisms have in common? They all have a nervous system. Some of them have a centralized, some of them have decentralized, but they all have a nervous system made out of neurons. And so based on that theory, we said, well, if the neuron is the basic building block of these biological intelligence systems, could we harness these neurons to do some computational intelligence for us? And all of this was kind of started out when, I had a previous startup before Cortical Labs called ClinicCloud. And in the twilight years of ClinicCloud, I was really interested in artificial intelligence. And I had been working on machine learning way back when I was even a med student doing my elective at Johns Hopkins. When I still remember when I was a research student, I had a really fun project, was looking at the use of video games and VR as non-pharmacological adjuncts for the treatment of pain, depression, anxiety in hospitalized kids. And my colleague at that time came back and, I was like, hey, where'd you go? He's like, oh, I went for a lecture. And I was like, what is it on? He said, machine learning. I was like, as if machines can learn. Mind you, this was way back in 2008, 2009. So anyway, that was my first introduction to it. I was really interested in 2018, 2017, and the hype at that point in time was convolutional neural networks. So image recognition neural nets. The issue with those neural nets was the fact that you were only as good as the data that you were training them on. And no one had more data than the big tech companies, so Facebook, Google, Microsoft, so forth. And so it was only a matter of time before, if you got really good at what you were doing that you'd be subsumed and consumed by these big tech firms. And we're really starting to see this now with the large language model like AI wrappers. So a lot of companies are now being eaten by ChatGPT, by OpenAI. So anyway, having looked at this, I was like, well, I don't want to do another convolutional neural net or X startup, and came across a paper written by Demis Hassabis, who's the founder of DeepMind, where he called for the greater sort of engagement of the machine learning AI community with neuroscience, because that's where all the initial discoveries were made. So I did exactly that. I took that advice, went to the Florey, and I spoke to the researchers there and said, hey, what's going on in this space? What's exciting? And they were like, yeah, we got this device, this multi-electrode array that can read and write to biological neurons. And I was like, wait, you have input output? Why hasn't anyone tried to do compute or program them? So that was the start of Cortical Labs. But anyway, so long story short, what we do is we take neurons and we play them on a computing chip. And because neurons communicate with one another using electrical activity, we can read that activity, and we can also provide them with a stimulus. And we couple that with a computer program, which takes the output of the neurons and moves the paddle in the game of Pong. It can be anything, actually, any stimulation, as long as there is what we call a structured information landscape, i.e. that there are rules that how signals are generated and given to the neurons that are affected by the actions of the neurons. So what we do, we take the outputs, put it into the game, moves the paddle. We then feed the information of where the ball is to the paddle back to the neurons, and we do it over and over. And we reward the neurons so if they hit the paddle, and we punish them or disincentivize them when they miss the paddle. And if you do this over and over 5 minutes, and with multiple samples, we can show that there is a learning effect in the sense that they move the paddle greater or with more accuracy over time to keep the game in play.
Fascinating. So you're Rick Sanchez.
Kind of.
From Rick and Morty.
Well, I'm not really. Brett is the Rick. I'm just. Who am I? No, there's no equivalence. Maybe I'm just Morty. Maybe I'm along for the ride.
Participating.
Fascinating. Do you think there is something intrinsic about human neurons that allows them to learn in a better, more efficient way than a traditional neural network?
Oh yeah. I mean, if you think about it, nature is really good at selecting for very fast neurons. Well, I mean, they're relatively slow, but in terms of processing, they're really fast and power efficiency. Because if you think about it, when it comes to energy and power efficiency, you can't consume more energy or more calories than you can eat, or you can hunt, or you can forage. So that's already a natural cap. And, you either get more food, which, is hard if you're a hunter-gatherer, or you become more efficient in how you use your energy. So neurons are very good at that. But secondarily as well, in terms of processing speed, neurons have to be really fast at predicting ahead of time what's going to happen. If you think about it, if you were, say, a hunter-gatherer in the savannah, and it took you the same amount of time as an artificial neural network to process if there was a tiger in the reeds, i.e., you needed like 2,000 samples and you're sampling at, say, 60 frames per second, you'd be lunch by then, right? And so we have this very good ability to predict ahead of time, to process hypotheticals in order to survive and to reproduce. So natural selection really does select for those two features that we think are what makes neurons, biological neurons, and maybe humans in that case, superior to artificial neural networks.
I'm interested by this because I suppose like the neurons themselves can signal very fast, but their ability to adapt in an evolutionary way would be surely slower than that of a computer, because you can run multiple tests in parallel with a computer.
Correct.
So how you were mentioning like that you're essentially training and rewarding or disincentivizing the neurons in a dish. How does that work, and how does that feedback then lead to the next progeny that responds in a more acceptable manner?
So with a computer, you have to bear in mind as well that all these simulations that they're running are actually running ahead of time and at accelerated speed. they kind of break down the moment you have to do it in a robot or something like that, where the clock is ticking at the same rate that we are at. So that's one thing to bear in mind. When we do our research and we look at the results, those are all in real time as opposed to simulated time. That's one thing that I think needs to be thought about. But the way the rewards, the incentives and disincentives work is based on a theory that's been developed by Professor Carl Friston at UCL. Mind you, we're not wedded to any one theory. It just seems to be the best one that explains our observations at the moment, which posits that all biological systems, particularly intelligent brains and so forth, are what are known as Bayesian generative machines. We generate hypotheses about the world ahead of time. So right now, you and I, our brains are making predictions about what the world is and our current, time right now. We don't realize it, or we don't actually even compute most of them because we have very good, strong priors about what the world is. For instance, you and I were not computing whether this bottle in front of us, is going to float because we have this thing called gravity. And so, if the brain is generating these hypotheses, right, it has to then be backed up by observation. So, if you think about it, the traditional neuroscience way of thinking is you have a photon hits the back of your retina then transmits information to the visual cortex, goes to the prefrontal, and then motor function happens or something like that. So it's this whole receptive loop. The new thinking in proposed cognitive neuroscience is that it's ahead of time. So we're predicting ahead of time what's happening. Then our observations, so the photon is hitting our retina, and then that is being compared against what the hypothesis is and what we're observing. And mostly, if we've got a very good model of the world, that's a usually one-to-one kind of correspondence. But if there isn't, then we have what's called information surprise. So now that we know that if the brain is trying to do is get very good predictions of what the world is, we can try to manipulate the neurons, i.e., like if they miss the ball, that's a bad thing. So we should be making the world more unpredictable. So we do that by infusing information in the form of white noise, because there's this thing called information entropy, and white noise has the highest amount of entropy because it's unpredictable. You cannot predict n number of sequences based from an observed sequence. On the flip side, if you do a good thing, we stimulate using a very predictable stimulus. So a predictable stimulus could be something like a sine wave, because if you think of a sine wave, if you hit on one period, you'll know n number of periods going forward. So that's a way we increase or decrease the overall entropy of the system from an information theoretic point of view.
So you've got these neurons that are sitting on a bioarray sensor. How would you sort of put it?
Yeah, so some of them are CMOS-based chips, so copper metal oxide sensors. So the same thing as your digital cameras. Some of them are sitting on glass chips where they just have electrodes etched into the glass kind of thing. They pick up the signal, and we can also reverse and provide a stimulus back.
Interesting.
Yeah.
So they're sitting on this chip, and then when they miss the paddle, you reward them. Also, you punish them with entropy.
Correct.
And then when they hit the paddle on the right spot,
yep,
you reward them with predictability.
Correct.
What about the neuron? That's just a fascinating idea.
It's almost like the neuron has a personality, yeah, and the neuron is responding to clean, predictable data.
Correct.
Versus something that is probably just overloading the system.
Yeah.
But so what about the neuron likes the predictability? Like, how does the neuron respond to the predictability?
By readjusting its outputs, because it's not one neuron, it's the network of neurons, and they all have to coordinate amongst themselves.
Okay.
Right? So because the way we do it is we encode information where the ball is to the paddle in an X and Y axis kind of way. So X axis is usually in the form of a rate encoding scheme, and Y-axis is in place encoding, and we stimulate certain regions on the chip with certain groups and populations of neurons. But those neurons are also connected to neurons that are on the motor regions that we then use to move the paddle up and down. So they're all talking to each other, really. And when they miss, the whole system gets, given that signal, or when they hit, the whole system gets given the reward kind of thing. So they're all trying to coordinate amongst themselves to get to that better predictability.
So how long does that take for it to receive the information and act differently?
So about 5 minutes.
Wow.
We see a strong statistical significance in the difference in the rate of return. So there are two measures in the paper that we looked at, which is the average rally length. How long can these neurons keep the ball in play? If it's single player Pong, that's the objective, right? Don't miss the ball. And then the other one is the number of aces. So is how many times does it miss the ball the first time round? Which, if you have lower number of aces, it means you're able to intercept it in the first go. And we show that with the right sort of training regime, they improve the return rate and also the number of aces.
Okay,
yep.
Fascinating. Now, in a traditional sort of machine learning sense, you would shift the weights and biases in such a way that you predictably know is going to increase the likelihood that the output is going to match the predicted or sort of the expected output.
Correct.
But the neuron doesn't really have that. So you just sort of reward it and it adjusts itself accordingly. Is that sort of the...
Yeah.
Okay.
Yeah. Because if you think about it, so in traditional machine learning, the improvement comes from the back propagation that happens of the signal. Where you have gradient descent and the network updates itself in the next forward pass to get a better result. In the biological system, there is a question of how they're doing it. We're not quite sure the exact mechanism, but mathematically makes sense in the form of having what are known as Markov blankets, so differentials in states between the observed world and the internal states of the neurons. There must be something that they're computing internally that is trying to reflect the observed world on the other side of the Markov blanket.
They're just intrinsically performing some form of gradient descent without us having to program it in. Is that what you're saying?
I don't even think they're doing gradient descent. They're doing something. They're doing some sort of ahead of time improvement or movement or change of their internal weighting structures.
Fascinating.
Okay. Yeah.
I don't quite understand it all. But
yeah, I don't think we do either. And all of these will take time to start thinking about how do we do better experiments and delving deeper into it. And I think this is really just the first step of us saying, hey, look, there is a very interesting observation here. Is it by chance? No, it's not by chance. Then if it's not by chance, then what is happening?
No doubt it's interesting.
Yeah.
I suppose from a pragmatic standpoint, you've got cells that are playing Pong.
Yeah.
What's the utility long term for something like that?
Well, if you think about it, we meant to train it to do something. What else can we train it to do? That's the big open question. And this is something my team is trying to work on at the moment. Well, not specifically work on it, but trying to figure out, is there a way for us to build tools that will allow us to program these neurons much quicker and easier so that we can open it up to other people to start experimenting with this stuff? Internally, we'll be doing our own experiments, but I think that we're limited by how much exposure and creativity that we have. We're pretty much mostly neuroscientists, stem cell biologists, some engineers, right? But there might be people out there with better or more interesting problems to solve. So that's if we go back, we can program them to do more than just Pong. Internally, we've done the jumping dinosaur game from Chrome. Well, the question that becomes is, what else can you get it to do? And especially if you can model real world scenarios using simulation programs that you feed information from the outside world with actuators out into the real world, you now have an ability to train these neurons to perform intelligence in a real world setting through avatars like robots or through digital avatars and so forth. So, it does open a lot of possibilities for real-time intelligence.
So you want to be the OpenAI of biological computing. Would that be a fair?
Pretty much.
Yeah.
Pretty much. Or actually the closest thing would be like the NVIDIA or the Intel, right?
True. Yeah.
We would love if there was an OpenAI. it wouldn't be us, but hopefully somebody else will build on top of this kind of technology. Somebody's got to, do the hard yards of building the hardware and growing the neurons, right? And I think in the current boom at the moment, the often unheard of company is NVIDIA, right? Because they're the ones that are powering everything, including Bard from Google and ChatGPT from OpenAI to the Llama 2s that are being trained by Facebook.
Perhaps one day the AI itself will utilize your technology to build a symbiotic human/robot.
Who knows? Who knows? I mean, maybe there are strengths and weaknesses, right, for both of these technologies. Now, the reason why I say that is that let's put it in a different. If we take a step back and rethink about it, our current AIs are so good at doing stuff because we've spent a lot of energy doing it, and also a lot of data. They're naturally very good at computation, the discrete, deterministic, like high precision math problems. On the flip side, we humans are really good at doing sort of like intelligence problems with very low energy, but we spend a lot of energy if you give us a very big math problem to solve. Suffice to say, what I'm trying to get here is that if you expend enough energy, you can get either systems to do things that they're outside of their comfort and specialty. And this is how we've gotten our current AIs to work so well, which is, a significant amount of energy has been spent along with data to train these systems. Now, the question is that a sustainable thing? I think it's going to be hard to continuously justify, data centers spending all that energy doing prompts and so forth.
Okay. So do you think there are applications for biological computing that will perform better on, biological synthetic biology computer interface rather than a traditional sort of silicon chip?
Yeah. So we have a paper that's currently under review, but it was actually a poster at NIPS last year. And in that paper, we did a head-to-head comparison against 3 reinforcement learning agents, A2C, PPO, and DQN. And we gave them the same game that we had our neurons play. And it turns out that in order to achieve the same level of performance, the reinforcement learning agents had to require a significant amount of samples. I.e., if you were to, say, play back the samples at a fixed rate of 100 frames per second, it would be in the order of hours of gameplay required, as opposed to 5 minutes that we had. So if you think about it from that perspective, the applications where this would benefit the most would be real-time applications. Things like robotics, things like cars, things like stock trading, and so forth could benefit from something like this. Energy efficiency as well is one of those things, right? We know based on just back calculation, back solving for how much cell culture media we use and how much of the concentration of that is made of glucose, that the neurons, for 800,000 to a million neurons, consume about 10 to the minus 4, minus 5 watts of energy. So that's a significant amount of energy saving, particularly really useful if your goal is to have something that needs a long time out in the field without needing to plug into the grid. So those are the 2 things that I think would be very useful, or 2 properties that would help with these things, particularly robotics and cybersecurity. But on the flip side, it's biological, right? And we've gotten it to do some sort of computation, some sort of intelligence, which is the functionality of what the brain is. It's a functional component, a functional aspect of the brain. If you are able to do this in a glass chip with neurons on the outside of the body that have been taken from patients or from people or whatever, because we grow them from human-derived adult pluripotent stem cells, you now theoretically have a model and ability to test for drugs, test for conditions outside of the human body.
Wow. So what's going through my mind at the moment is that in vivo in the human body, when signals are sent to the brain and the brain responds, signals are, I suppose, propagated and sent through the brain using electrical signaling. as well as chemicals that influence the way that the brain operates.
Yes.
So in that sense, how would you kind of mimic that chemical response that influences the brain's activity?
So if you grow these neurons, right, from say the stem cells do secrete their own neurotransmitters. The question is, what are the right proportions? How much excitatory, how much inhibitory, unique glia, so on and so forth. Well, our work shows that, there's a good proportion that you should be aiming for, and also glia is really important. So we can theoretically grow a brain from adult pluripotent stem cells, and people are doing that with organoids, like mini brain structures. And they have some very interesting sort of firing patterns and so forth. So yeah, you can actually just recreate a lot of that in a dish. The question then becomes, how do you test for their functionality? And it's easier with the other organs. So for instance, if you grow a cardiac organoid, you just see a beat, you can measure contractility for muscle. Kidneys, you just measure filtration rate. What does the brain do? And one of the problems is that we've been measuring spiking activity, how many spikes is happening with these neurons. The problem with spikes is that they don't really tell us anything besides, hey, a message was being sent. And we know for a fact now that, not necessarily the more spikes you send, the better they are. It's a analogy that I make, which is that if you could be in, say, the MCG and you're listening to, you're in the MCG and you're trying to listen to stuff, but you can't because there's so much noise, right? So you have a lot of noise activity, but not much transmission of information. On the other hand, you could be in a lecture theater and you'd have only one person speaking, but the amount of information being transferred is significantly higher, even though it's only just one person speaking. So measuring for spikes isn't, I think, the end-all and be-all on how we figure out what functionality of these neural organoids are. The way we measure that functionality is by putting them into game worlds and testing them. You put them in a baseline Pong world, see what they do, and then you start squirting drugs in, see what happens. Improvement, decline. And then on top of that, what's really interesting is you can start thinking about CRISPR conditions. And could you CRISPR, a sort of known familial dementia and get a dementia model? And then from there, test your drugs on that. I think that is the most exciting part of this new synthetic biology wave. And the other really interesting factor is that particularly with any drug that crosses the blood-brain barrier, anything that has any CNS sort of effect, there is a significant amount of unknown when it comes to the cognitive side effects of these medications. So things like antipsychotics, anti-epileptics, depressants, even chemotherapy. One of the main reasons people discontinue from these drugs is because of the fact that they have brain fog and that the treatment is worse than the condition, and so they discontinue it. Now, it wouldn't be great if we could figure out what the brain fog effect was like before we gave it to the patient. If we could take some of their own blood and turn them into stem cells into brains from there, and then test the drugs on those things, that would say, okay, so there are 6 different antipsychotics. We've tested all 6, and candidate number 4 gives you the best result with the minimal amount of side effect. Right?
Okay.
That's personalized medicine in a nutshell.
Yeah, I mean, it's got a lot of utility in the research space.
Certainly.
There's no doubt.
And clinical as well, hopefully, once we're able to prove that strong in vitro, in vivo sort of correlation.
Okay. So you take differentiated cells, you induce them to become pluripotent, then you take them down the sort of neural pathway.
Yep.
You turn them into neurons, and then you insert some high-risk gene for Alzheimer's using CRISPR. Then you get it to play like a memory game, and you squirt
something, and it
drugs.
forgets to play or something.
Yeah.
And once you measure its output.
Exactly. And once if you can show that they actually have a decline over time, you now have a model.
That's so fascinating.
So then you just take all the compounds and drugs that you have and just try them one by one and see what happens. Maybe you'll find one that just stops it or reverses it.
I remember learning about organoids a couple of years ago, and I was very much sort of fascinated by the idea that you could have sort of much better models of disease states than traditional cells. But then I never considered what a poor model of what a poor model an organoid is of the brain. Like, how do you measure the effect of a drug on a brain organoid? Like, how do you know what the brain is experiencing?
Well, I suppose this is the way, right?
Yeah.
So this is one of the insights that we've made over this time, just observing it and experimenting with it. Is that we started to realize that we might have an in vitro cognitive testing system on our hands.
Such a brilliant idea. I'm curious, like, surely, you've got a lot of traction from this, just meeting new people. Who are some of the people that you've met because of the project you're working on?
Who are some of the people we've met?
Like notable people. People you meet, you're like, wow.
I think you met the Amazon CTO.
Yeah. So Herman Hauser came down to our lab at the start of this year, and he had a chat. He had a look at what we were doing, and was quite interested. So that was a good one. I've met some really interesting people along the way. So Dr. Herman Hauser, he is actually the chairperson of BitBio, which is a company that we work quite closely with. They do a lot of CRISPR stem cell lines. He's the founder of ARM. So he's also a well-known VC venture capitalist in Europe. But there's a whole bunch of really interesting people who I've met. It's hard to remember. There's a bunch of them. I met Demis Hassabis, who's the founder of DeepMind.
Oh yeah,
right.
Yeah, really interesting discussion. I was actually just at this Brain Mind Summit about 3-4 weeks ago in San Francisco, and I caught up with Tom Oxley. He's the founder of Synchron, Stentro, local Melburnian, but really proud to see an Australian company beating Elon to the first human trials for BCI.
Yeah.
And also Reid Hoffman was there as well, so had a chat with him. But Reid was more interested in the AI aspect of things because he does have an AI startup at the moment.
Is it Hey Pi or
Pi?
Yeah, Pi.
Yeah.
Yeah. Such a small world. Wow.
Absolutely.
Yeah.
All right. Well, I kind of we'll go into your story and your background a little bit more, but I was curious about the sort of energy savings that you mentioned with sort of biological computing as opposed to a traditional silicon chip. Can you sort of go over that again? What's the percentage savings on energy for specific tasks?
And how does that work?
So, I mean, it's a indirect measure as well. I mean, we need to do more work around this, like formalized calorimetric testing and so forth. The way I did it was essentially back solving. So what we usually do with these neurons is we do a regular cell culture media change out every 24 to 48 hours. That's like a 50% removal of the fluid and replacement. That's about I think 10 mils of cell culture media. So if you know what 10 mils, so what kind of solution you use for 10 mils, and you know what the osmolarity of the glucose concentration is, you can back solve for how many moles you have, and then you can do the combustion, and you can figure out how much energy is actually in there. So this is assuming 100% combustion of glucose, in that period of time, which is already an overestimation. It's probably closer to 10 minus 6 minus 7 watts of energy, if we were to actually really do a proper calorimetric testing. So that's how we work it out. Now, the comparison for that would probably be, the closest thing would be like a solar pocket calculator. Now, a lot of people go, well, I can train Pong on my GPU to do all these things. I was like, yes, you can, but can you do it on a solar powered calculator? That, I think, is the true measure of the efficiency of a system like this. And the other side effect is that they don't heat up, which is great, because the vast majority of the energy consumption actually is not just in the training, but it's actually in the cooling of the system. These GPUs produce a significant amount of heat, and it has to go somewhere.
And then you were also mentioning sort of real-time applications like robotics and self-driving cars. I suppose, if I have this right, are you saying that these neurons can learn in real time, whereas traditional machine learning methods require you to collect a bunch of data and then train a new model on GPU clusters? Is that
pretty much?
Yeah,
you can do that. And If you think about it, ChatGPT only got so good because it read the entirety of the internet, right? We're never going to be as good as ChatGPT, right? Because it's read everything. But to get to some level of actually being a pretty good large language models, you have to read a lot of stuff. Now, if you think about it, a child gets pretty good at language, even though they may only have 3-4 years of exposure to the real world and some language. So there is a significant saving in terms of sample or information required, even in biological systems when compared against, the large language models that we have. I mean, I haven't seen a small language model yet, so we'll see.
So, Hon, what do you actually do at Cortical Labs? Let's talk a little bit about what you do.
What do I do? So I'm the CEO and the founder. I do everything that isn't being done by other people. So right now we're a very engineering heavy company. So I do a lot of ops. I do a bit of marketing, hence the reason why I'm here. A bit of PR, that kind of stuff. I help set goals and strategy and try to do, the fundraising when required. So that's, I guess, what entrepreneurs really do, right? As a founder, you're just doing everything you need to do. And as you get larger, you start to hand over more of the management to other people who are probably better off, dealing with, say, technical or management kind of stuff. But you're always there, trying to give advice and align everybody to a common strategic goal.
What do you think one of the biggest challenges, like running the company, has been so far?
Well, this is a very hard technical and scientific problem. So that's been a challenge, and finding people to help you on this journey is actually really hard, because you need a lot of very highly specialized skill sets. It's also really hard to convince people what you're trying to do because it's so complicated, right? Like, I have 6 layers of how I have to pitch this stuff, whereas if we were doing a simpler startup, it could be like, well, I'm doing an Uber for X, or I'm doing a ChatGPT for Y. That's the simpler way of pitching a AI startup today. So telling people the story is hard. Inspiring and getting people to come along for the journey is hard, but it's really worth it because of how interesting and unsolved the problem space is. So yeah, it's a mixture, really.
I think as founders, we usually start off creating the company and everything is our idea. All the input, the intellectual input is coming from us. And then as the company grows, you become increasingly disconnected from like the engineering and sort of technical problems that arise, unless you're Elon and you want to join every single engineering meeting. Do you find that that's been the case with you? Like, have you become disconnected from the core engineering problems that the company is trying to solve?
Well, I'm still familiar with the core engineering challenges and the problems. I'm just not so well versed with the details anymore. So I understand overarching what everyone's doing and what are the problems we're facing. Sometimes the solutions that are being worked on, I'm not particularly familiar with it, or the the results from particular experiments. I think it's really hard to know everything, and I don't think even Elon knows everything. He cherry picks his particular interests. A project like the size of SpaceX, I'm sure, has a lot of moving parts, and he may know a couple of things about maybe the propulsion system, but there are other things like the hatch door that might be a technical challenge that he may not be bothered with, right? Because it's less sexy and less interesting, but still an important detail. So yeah, to answer your point, I don't know everything anymore, but I still have a pretty good grasp of what's happening.
How many employees does Cortical Labs have?
I think we're up to 17 now. Yeah.
What's your method to hire people? High quality talent.
Method is actually somewhat variable. So sometimes when we do need a need for, say, particular engineering or scientific talent, we put a job ad out. And then, we interview, we bring them in, we gauge their interest and suitability. Other times, we just go headhunting on LinkedIn. What's this person doing? Are they interesting? Can we use them? Can we get them in? Kind of stuff. So it's a mixture, really.
I suppose one of the things that we're struggling with at our company is Like, how do we find good talent? And then how do we screen good talent when that talent is specialized in things that we're not even specialized in?
Yeah.
Do you have an approach to doing that?
No, unfortunately. I think this is still the holy grail of startup HR 101, right? Like, how do you find the best talent possible, right? And retain them, particularly in areas where you're just not strong, and that's the reason why you're hiring, right? I think, you try your best. You're not going to get all of them right, but if you can, do say 60-70%, you're betting above the average. So I wouldn't get too hung up about making bad mistakes. I think every company does. The question more so becomes like, if you've done it, can you identify that early and mitigate issues with the wrong person for the job kind of thing?
Yeah.
Fire fast.
That's right. Just SF style. So you mentioned that you have different, pitches. You have different ways to pitch the idea depending on who you're talking to. How would you go about explaining Cortical Labs to someone who you may be interviewing versus an investor?
So usually with the interviewee, we usually bring them in if they're in Melbourne or on site, and we say come in, have a look. Seeing is believing. It's very hypothetical, and because of the various layers of what we do, it's very abstract. People don't quite get it until they see it. So in order to make sure that somebody really gets what we're doing, we bring them in and we say, this is what we're doing. Have a look. Those are real neurons. That's a computer. That's a chip. They're all connected. And then they usually go, oh yeah, whatever. And then 3 days later go, oh wow, I really get it now. There's a really strange lag effect, latency that we see. Investors is the same thing as well. Some investors are really good. They can just see it. They're like, cool, I get it now. I don't need to do any further. Sometimes, it doesn't take them, it takes them a while, and, we bring them in, they have a look, and they also have that latent effect. Like, now that I've been thinking about it, it makes a lot of sense. Like, yeah, that's like last week. They're like, yeah, it took a while. So I think, because we're in the physical hardware space and the wetware space as well, having the ability to show these things happening helps bring this beyond just a sci-fi kind of thing to like, no, this is really happening.
I think I'm really curious about how this idea, I mean, we sort of know how this idea got its start. You mentioned the paper that you read, and I know there's a technical co-founder involved here as well. Like, before you had this lab and before you'd put the neurons on the chips, how did you convince people that this was something that they should join you on? How did you get that initial start?
Good question. It was more like, wouldn't this be really cool if we could do this? Right?
But did people have skepticism in the beginning?
Oh, 100%. Everyone was skeptical to begin with. But, there are some people who are curious and, want to see things happen. So, for instance, our first check came in sometime around May 2019 when I pitched the idea to Nikki Skivak, who's the founder at Blackbird Ventures. And it was so wacky, but he said, this is so cyberpunk and cool. I just want to fund it. So he funded us, right? and I had Andy, and I also I had a previous startup, so I still have people who I wasn't connected with, and I brought them along with this new journey because they're like, well, what are we gonna do now? This looks pretty fun. If you can get money, let's go do it.
Okay. Yeah. So who was the original founding team other than yourself?
So it was myself. Andy Kitchen was my CTO. He was from Clinical Cloud as well. Andrew Doherty, he's my chief hardware engineer. He was also from Clinical Cloud. We had a couple other people from Clinical Cloud. But we kind of shrank in size to a core of about 4 of us for the first, 18 to 24 months. Mind you, we also had the unfortunate event of raising and then going to COVID lockdown. So really couldn't do too much. We didn't have enough money, and executive decision was made to jettison all PR, marketing, all non-essential parts of the business and just focus on using whatever money that we had to do the experimentation required to show, without a doubt, that these neurons were doing something.
How did you determine the initial amount of money you raised?
How did we determine it? It wasn't actually determined by us. It was determined by the investors.
Sure.
They were like, well, here's $1 million, and you happy with the valuation? We're like, I guess, yeah. And most of the time, it's interesting, like if you think about like fundraising. So, different investors have different strategies. Our most recent one was, they set the valuation. They go, okay, here's your valuation. Ask for how much you want. But mind you, the more you ask, the more you dilute yourself.
Fair play.
Yeah.
Okay.
As opposed to the other one, which is ask how much do you want, and then I'll figure out what the valuation is. They went around it the other way, which is, this is what we think you are worth. And you can ask about how much you want.
So this was Blackbird that gave you the valuation?
No, this was Horizons Ventures.
Okay.
Yeah.
Okay. So did you, I want to know sort of your approach to fundraising. How did you go about your initial fundraise? Was it just an idea? Like, did you have any traction at the time?
No traction.
So it was just a pitch?
It's just a pitch.
So you didn't even build anything?
I didn't even build anything. It was a hunch.
So did you leverage the previous company you were working with?
Not really. So, I mean, this is a funny story. Like in 2018, I went up to Hong Kong and I met with the partner at Horizons, and I was pitching him this idea, and he's like, yeah, at Horizons, we're known for doing crazy investments, but this is too crazy for us. But good luck. But, it's interesting because you never know where the connections you make today will lead you down in the future. And one of my advice is always to try to increase the number of random chance encounters that you have, because that's the only thing we have any control of in the world that we exist in, right? We can only increase those number of random chance encounters with the hope that it actually leads down to more interesting and less predictable paths, because those are the ones that give you the most amount of return, right? High risk, high reward kind of thing. Mm-hmm. So I saw, the partner in Hong Kong 2018 said, nah, this is too crazy for us. But then in 2021, when we released the preprint and that got some media traction, he came across the paper and he's like, I got to get in touch with these guys. So in 22, we started talking about, let's do a deal kind of thing. And so, something that had written off in 2018 because it didn't go anywhere became a thing in 2022 because we had more traction, we had more evidence, and, they had inside early information about what we were working on, as opposed to other people who were just learning about it.
Yeah.
So the game is it's a game of information, right? Investments, startups, it's an asymmetrical information game. Some people know more, some people know less. The ones with the most amount of knowledge are the ones that are able to execute better.
Okay. But this was still post your first fundraise, is that right?
Yes.
Yeah, so your preprint was after your first fundraise.
The preprint, yes. After the first fundraise.
Okay.
So yeah, the first fundraise was just crazy. Like I just went up to Nikki and I was like, I have a hunch. Hey, you believe that dogs and cats are smart. They all have a brain. It's the same thing I was telling you guys. They all have a brain. They're made from neurons. Wouldn't it be cool if we could just get these things to compute because we have read and write?
Yeah. You had a pitch deck though, right? Like surely you had a...
Oh yeah, I had the
backdrop.
I had a pitch deck, but it was like when you're doing a pitch deck at that point in time, you could put anything in. You could put even a picture of the Matrix in and people would be like, oh, okay, I see.
Deep tech.
Yeah, exactly. You're like, I know Kung Fu, or, oh no, this thing that goes to my head, or whatever. Like,
wow, inspiring founder.
It could be anything really, but I think it was more about the idea, and, it was luck. Mm. A lot of startups, and we're still in the luck phase as well, right? Like in the early days, if you ask any like C-level investor, they always will say that it's 100% luck in the early phases. And apart from that, the only thing as a startup founder you can do is not to screw up, right? The default pathway is did the founder screw up? Yes or no? If yes, then that's the end. And no, then you ask, were they lucky or not? Then once they start building traction, they have multiple rounds, then it's less about luck and more about, execution. But in the early phases, it's kind of like, yeah, how lucky are you? It's like baby turtles when they hatch. It's all about luck, whether one makes it to the ocean kind of thing. But once they make it to the ocean, they're usually, a little bit safer and there's more higher chance that they succeed.
Interesting.
Okay.
So you started as a medical student, is that right?
Well, yes, my really early journey started as a medical student.
What was the intention doing medicine?
I I actually wanted to do medicine right from the beginning, and I ended up getting a good ATAR and applied for medicine and got accepted.
Straight in.
Yeah, as an undergrad. So, also my brother's a surgeon, so there was family thing going on there. But it was. I actually think it was a really good piece of training. In fact, I would say one of the best training you can have as an early stage founder is to work as an emergency doctor.
Why is that?
Putting out fires all the time.
pressure.
Yeah, you're putting out fires all the time. You're always resource constrained, so you're always having to triage, right? And there's always something more important that you have to go deal with. There's always a crazy amount of negotiations that need to happen because you have crazy patients all the time. So being an emergency doctor, I think, was actually really good training for running an early stage startup.
So you finished medicine?
Yeah, I finished medicine.
And how long did you practice for?
I practiced for about 2 years.
Okay.
Yeah. But a lot of it was just doing ED rotations because, that's the generic pathway most people do. Once you've done your med and your surge, everything else is just ED, really. And I also worked in some of the craziest EDs in Melbourne. So I was in Frankston. So Frankston Emergency Department on a Friday night. We used to call it Franganistan.
Yeah, that's right.
Yeah.
That's right.
Well, I'm curious, like you finished medical school and a lot of people by then have this sort of sunk cost fallacy. They've spent all these years learning medicine, but then you suddenly transition into the startup world. Like, how did you justify that to yourself? What was the process that went on in your head?
Well, I mean, the thing about it was I never really intended it to be like transitioning out. It was more of I'm going to take a break from med and, it's always there if I want to go back. Except that has turned into a very long and extended break. It was always a fallback. But, I don't think it was a sunken cost fallacy, right? A lot of people think that it is, but you learn skills in medicine that are quite transferable. Maybe not on paper, right? Like, no one cares if you can, suture up a laceration when I guess that'd be useful when you're doing like a manufacturing startup. But anyway, like no one really cares. But the training you get for like empathy training, talking to patients, helps with negotiations and so forth. So, there are soft skills that you pick up along the way that are, I think, universally applicable.
I'm curious though, because before or behind the scenes here, we sort of were discussing this, and you mentioned there were some drawbacks to medicine, that you can become very myopic, very sort of monocular with the way that you view the world, and sort of very uni-skilled. How would you sort of contrast these two almost like incompatible views that you've shared? Yeah,
so the formal training of medicine is very myopic, very non-transferable, right? So, and this is usually the case with specialist training and also in the university system, right? For instance, it might have changed now, but when I was doing med in this university, I remember we were exclusively only in the med corner of the university. We would have lectures only amongst ourselves. Well, I guess there were some physios and some dentistry people, but I was pretty much stuck with the same group of people for 6 years. So I didn't really have diversity of like meeting other people in engineering or in business or in arts or whatever, right? It was pretty much just med. So your worldview became very closed up very early about what the rest of the world looked like. And you end up in very interesting sort of microcosms, little fiefdoms of like, oh my God, so-and-so professor is like God. And you're like, well, actually he's not, because he's just somebody who works in med and highly respected. But on the street, he's just like an average person, a normal person. So you get in these very small views of how the world is. And I think what's really interesting is to be able to look beyond that and realize that there is a really big world out there that is beyond just doing medicine, that is beyond just even medicine in Melbourne, right, or in Australia, that there are huge amounts of opportunities in applying what we know in medicine to other spaces. So I think the training is is myopic, but it's very good if you can break out of that.
What was the thought process like when you had the realization that maybe you want to try something different? If you were stuck in this cosm,
yep.
How did you think about it?
So I was already exposed to this alternative sort of landscape very early on. So in the Melbourne Medical Program in the early days, you would do, I think, 2.5 years of preclinical, and then you do a year of research. We call it the AMS, Advanced Medical Science year. And then you come back and you do your clinical years. In my advanced medical science year, I was in the US. I was at Johns Hopkins. I was already doing something very non-traditional. So I guess I already had the inkling of doing non-traditional pathways when I signed up to do research with VR and video games for pain, depression, and anxiety research. My supervisor at the time was also very entrepreneurial. So he would have ideas about building apps or services, and he would take me on trips to San Francisco, and I was exposed to this whole space of wait a minute, what are these people doing? Oh, they're software engineers. How are they getting paid? Oh, people just give them money because they have ideas. I was like, wait a minute, is that even a thing? And yeah, I was exposed to this world where you had people who were willing to take bets on interesting ideas that you could, with the right amount of skill and storytelling and organization, build companies, right, that could change the world. So that was how I was sort of exposed to this, and I had a slightly different view of the world at that point in time. I already had built contacts during my time there. And I remember in one of the early contacts I had, I can't remember who it was, but they were saying, oh, you got to go to South by Southwest. And I was like, why? Because they're that's where all the cool investors and tech people are. So in, 2014, I convinced my co-founder at the time, Andrew, who was also a medical doctor, but he left much earlier and just went to work for Bain as a management consultant, to join me in this startup journey. He left Bain. I put medicine on hold. We had a prototype digital stethoscope device that we had built, and we booked a flight, went over to the US, and went to South by Southwest with the prototype. Then we just spoke to a whole bunch of people, and came back with a bag of money from angel investors. So it's kind of incredible. I look back on my journey and how we were able to do that, and the fact that some of the learnings I still have, which is don't go for any of the day events because all the deals happen at night in the parties.
Interesting. So what was your approach when you went to places like the US? Did you have a methodology to organizing meetings, or did you just go there and think, I'm just going to wing it?
I've done both. So there's this road in Palo Alto called Sand Hill Road, and that's where all the US VCs are based. So you have Coastal Ventures, Andreessen Horowitz, and so forth. I still remember we were this was in the first startup, and we were kind of poor, so we were let's save on the Uber. So we walked up Sand Hill Road, and never again, because it's quite a steep hill, and you get there and you're hot and you're sweaty and you just can't focus. So we literally one point just went door knocking. Hey, we're these Australian guys with an idea for this thing, can you fund us? And it turned out that wasn't the best way of getting things done. A better way was to get introductions. Warm introductions were always better than cold, and you would then try to organize a time, and you would get tips from friends and people who'd done this thing for longer about what you should and shouldn't say in your deck and your pitch kind of thing, how you structure and organize it. Because if you think about it, if you take the perspective of a science person, you're oh, the more information the better. So I'm going to cram 30 slides in with all this detail. When in fact, no one in the investment space has the ability to think about all of that stuff, and you're actually doing yourself a disservice. So they always, and it's a fair point, always say keep your decks to 10 slides, max, size 24, 30 point fond and sell the story. Tell the story, not the details. The details can be figured out later on once you've convinced somebody that this is a story that they're invested in.
Absolutely.
So this sort of trip up Sandy Hill, was this for the stethoscope startup or for Cortical Labs?
Oh, for the stethoscope startup. I'm never doing that one again.
Okay. So, but you did end up coming back to Australia with a bunch of money.
Yes.
For the stethoscope startup.
Yes.
And I'm curious, like you were an Australian company. Were you registered? Like, so how did they give you this money?
So we were an Australian company, but then, through contacts and, it's funny, people you meet and you reach out to, they advised us to flip to the US. So we flipped the company to a Delaware C Corp and, turn the Australian company to a subsidiary. So once you have a Delaware C Corp, you can take money from anywhere really, because everyone knows what the rules are as a C Corp. And we essentially took the angel investment money to build out more prototypes. And I think it was put to a Kickstarter or Indiegogo. I can't remember, one of those things. And so we did a Kickstarter / Indiegogo thing. And that caught the attention of some really big name investors. So we had Tencent and Ping An Ventures. And this was in 2014, 2015, who were like, this is really cool. Here's $5 million. Go make it happen. Yeah. So we raised $5 million on, I think it was like an uncapped convertible note. It was kind of crazy. And we took the money, we built product, we got it FDA CE certified, factory line in China. We're making devices and software and backend. The only problem is that when you take venture capital money, you always have to grow and grow fast. And, we made the mistake of taking too much too early. And so in order to raise the next round, we always had to, I call it chasing the dragon. We had to, keep going for a larger customer. So we started out with a B2C deal with Best Buy and I can't remember who else. Anyway, Amazon. And we were selling devices, but not enough. So we tried going to a B2B scenario. We're selling to employee health programs. This is all in the US. And, that wasn't like, giving us enough revenue. So we decided to put our eggs in one basket and, instead of hunting rabbits and deer, we thought we'll go and hunt the elephant, which was the VA. So we had partnered up with a subsidiary from Intel where we had done a deal to sell a stethoscope and thermometer along with something else. I can't remember what it was, like a kit to the VA. And the VA had placed, I think, about a 10,000 unit order. But this was in 2016. And what happened December 2016? Donald Trump gets elected. And, his threat of tearing up Obamacare really shook the whole landscape because, the devices that we were going to sell were part of a trial program for an employee health. Sorry, it's part of the discretionary expenditure fund for the VA. And, the last thing you want to do when you don't know where the money is coming from is to spend your discretionary expenditure fund. So, we spent a lot of time waiting, and, the point we decided was not worth waiting because we're just burning cash. And so we decided to just close up. And that was the bookend of that startup.
Wow.
It's an awesome story.
It is.
Yeah, it's like the scene from Silicon Valley where they're in the office and they're selling off the furniture. Been there, done that.
Wow.
I love it. So this digital stethoscope, was it something that like I could have bought instead of a cardio paw from Littman?
Yeah, 100%.
And it's dead because of Trump.
Well, kind of, yeah. Well, we didn't have enough money to keep it going, and it was meant to be more of a mass consumer device rather than a diagnostic system. It was quite interesting actually, because what we also did some work with the women's hospital, and we actually developed a pretty interesting algorithm where one of the problems that the neonatologists face over there is needing to obtain heart rate within the first minute of life as a determinant of whether you aggressively resuscitate a neonate or not. And neonates, as you know, are peripherally shut down, so you can't do pulse oximetry. And they're also wet, so ECGs don't stick very well. And so, the idea was, could we use a stethoscope that could count the oscillatory beats to figure out what the heart rate was? And actually, a trial was done, and it was quite successful. I don't know what happened. I got to go fall out one day, where our device was placed on these newborns, and we were able to pick up like very accurate heart rate within that first minute of life. But yeah, it wasn't enough to cover the bills.
Fascinating.
So what did it look like when you had to close shop? Like, you had already spent a certain amount of money.
Yeah,
you had investors who were probably like,
it was tough.
deal?
It was tough. Like one of the lowest points in my career. It's demoralizing because we also had raised too much money, so we had like $1 million left in the bank, and we didn't have enough to do a new product line. We couldn't do any more hardware. We had a difficulty, trying to figure out what to do. Some of the investors didn't want their money back because they had written it off already. So we were just a zombie company for a long while. People would come in, they would just watch some YouTube, and then they would clock out, kind of thing. and yeah, we were rudderless for a long time. And actually, that was one of the worst parts. I was like, I had much rather we just ran out of money and we just closed up naturally and say, we're bankrupt, we're out of money, bye. As opposed to just trying to like struggle and figure it out. And that's one of the dangers of raising too much money. A lot of people say you can never raise too much money. I say bullshit. You can always raise more than you need. And that becomes a dangerous thing because you become unfocused. You also have the problem of, having very high expectations for your next round. You run into a lot of problems when you raise too much too quickly. So that was quite a low point, but it's a learning experience, and you get better. You learn a bit more humility, a bit more experience when it comes from that.
Lesson for any founders watching: if you get an email from Tencent offering you $5 million, reply,
take one.
I just want 1.5.
We'll take 1.5.
I'd like to come back to something you said earlier on in the conversation about sort of increasing your surface area for serendipity. Obviously, you are a strategic person, and I'm sure that you thought relatively deeply about how to position yourself in your life to, I guess, anticipate and take advantage of the trends that were taking place and to become a CEO of a successful company. What did you do when you were young that you think was the most high yield to get you to where you are now?
I think it was when I taught myself how to code. Not so important now because you got ChatGPT to do all your coding for you, but like in the early days, being able to code for something by yourself was huge, right? And in many cases, if you think about what a startup is technically a cult. And in order for you to attract cult members, you got to perform some miracles. So being able to code and build like early MVP prototypes was a huge boon because I could build something and go, guys, look, it works. Now please come help me, like build a real product kind of stuff. And I think that was one of the best use of time when I was in high school. Just learning how to code, understanding how systems are built and put together, and being able to communicate to engineers and say, guys, it's not impossible. I built this thing. I just need you to help me build more of this stuff. It's much stronger when you do that, when you're looking for engineers to join you, because engineers are usually quite skeptical people. But if they see you have some technical chops and you're able to like execute as well, it becomes more attractive for them to work together with you.
When did you actually do this? Like, was it during your medical degree, before, after?
So, I was coding ever since I was like 14 in high school, and then I had a pause because you had to do year 12 and all that stuff. But I picked it back up again and it's interesting, like the story arc, because when I was in high school, I was one of those weird kids with a Mac, and everyone else was using Windows. There weren't enough apps. So I had to teach myself how to code. Now, back in the old days, the Mac was coded in a very weird language called Objective-C. And very few people knew that. Now, we fast forward to 2006 or 7, first year of med school. The iPhone came out. And I was like, oh, this is so cool. I got a mate to like ship it over from the US, and I jailbroke it and activated it. And then there was also an underground community of people mucking around with the iPhone and building apps. And I somehow got into it and I looked at it and said, wait a minute, these apps are built using Objective-C. I know this language because I had to do it for my Mac. So I started building apps when I was in med school. And that was a bit of a side hustle. So I was building apps in the early days and, doing some consulting work and stuff like that.
This was prior to Swift.
Prior to Swift.
Yeah. Okay. Fascinating.
Absolutely. It's almost synonymous with, what's happening now with OpenAI.
Yeah.
Looks like they're trying to create a little bit of a, app store themselves. So a lot of people will transfer their skills into that space.
100%. Except now it's more about, data, pre-training and so forth.
Yeah.
Well, I'd love to know a little bit more about your childhood as well. When I was a kid, I had some eccentric habits, and I'm sure Oliver also has his own eccentric habits. What were the things that you think made you different as a kid? When you were in school, or what was like different about you or your interests that maybe wasn't sort of seen in your classmates?
I think I had a very actually typical childhood. I didn't have anything too eccentric. I did have the propensity to break things because I would try to disassemble them and put them back again. So I guess I was trying to be a natural early born engineer. I remember getting into a lot of trouble, cracking open the family computer and breaking it. But the benefit is you got to learn what went wrong and how to fix it. And so I think that was one of the early traits that helped me go down this path.
Did you ever experience pressure at all by your parents or family members?
100%. I'm Asian. There's always pressure. It's the pressure to succeed, to live up to expectations, that kind of stuff. So, I remember like year 12, that was one of the most highly stressful years. Primarily because I don't know, I just had my mind out. I wanted to get a med. But to get into med, you needed like an 8 out of 99 and above. And so I worked really hard to try and get that. And I remember when the results came out, it was like a really nice, slightly overcast day, 24 degrees. And I got my results and I felt really happy with it. So I went to the Botanic Gardens and I just like lay down on the lawn and had a nap.
Nice.
Yeah.
So when you finished medical school, your parents would have been really proud of you. You were practicing as a doctor and then you were like, I'm going to try something new.
Yep.
What was your parents' reaction to that decision?
Near disownment. They were like, "What are you doing? You can't do this kind of stuff." I was like, "Well, I'm going now. Bye."
How did you deal with it?
Well, okay, it wasn't that bad. It was more of like, "Are you sure about it?" And I was like, "Yeah, don't worry. There's always a fallback, which I can always go back to," kind of thing. So they weren't. I wouldn't say fully supportive, but they weren't like freaking out as well because I had finished, right? Because I experienced actually early on. I was like, hey, I don't know if I want to go all the way to the end. And my dad actually gave me some really good advice, which he said, you can always learn how to code, right? You just get a book and just teach yourself. You can't learn to do med because you need to be in a hospital. You need to see patients. You need cadavers to cut up. You need, physical things. So I stuck around with it and finished and worked just a bit. So there was less pressure, I think, because they were like, well, we've done our best. You have some professional degree in training. Worst case scenario, you just go back and intern or be a resident kind of thing. So that was it. But, one trick is if you're a founder and you're from an Asian background, your parents are disappointed, just do some PR. Once they see some newspaper stuff, they're like, oh, you're actually doing really well.
Wow, you're famous.
You're famous. Exactly. That's the hack.
Incredible.
Yeah. And you're like, well, I still have to pay the money anyway for the PR to get like the marketing out there. So, it's a win-win situation.
That's so true. Yeah, I have a very similar story of when I got my ATAR results. I remember the university sort of called me.
Yep.
And my mum was in tears. And then now with I'm planning on stepping aside from medical school, and it's very much the same thing. But when they found out that we had an interview scheduled with Forbes, they changed their mind.
Yeah,
they were like,
100%.
"Oh wow,
Yeah.
it's kind of cool."
Exactly.
Absolutely.
Because they get to go. I think it's a lot of it is about how are they going to explain to their friends what has happened.
Exactly.
Right.
Yeah. my kid goes to this and this, and
Yeah. What does your kid do? Never mind that. He's on Forbes. And they're like, oh, it must be doing really well then. Yes.
Yeah, it's an interesting mentality. It's like a protective reaction from the parents. They just want what's best.
Yeah.
They're just worried.
It definitely is the case. And I think a lot of the times, even though they're supportive, they mostly just don't understand what we're doing. My parents have no idea what I'm doing. As far as they're concerned, they're like, well, Forbes wrote about it, so it must be important. And I've tried to explain them many times. They're not from a scientific background, so it just goes right over their heads. But they're supportive, and I think that's key. You always have a support base.
Well, I think it absolutely is key. I feel the same way to some degree. Like my dad is a tradie, so he didn't have a formal education per se. But when I speak about some of the things I do in the lab during my PhD, or even with the company with Ben, he just goes, I believe in you.
Yeah, exactly. I don't know what you're doing, but yeah, it must be cool. Yeah.
I suppose I'm really curious about if you had like a vision growing up. You may not have had this idea or this sort of iteration of the idea, but was there like some guiding principle of, I want to transform this industry, or I want to make as much money as possible? What was a driving sort of force?
As a kid?
Or as a kid and sort of...
I guess as a kid, everyone just wants to drive a Lambo or something like that, right? So it's always like, hey, wouldn't it be cool if I was rich? And then as you get older, you're like, yeah, money is nice, but it's not the most important thing. And actually, you come around it and you're like, actually, the more important thing, at least for me now, and maybe it's just, getting older and just observing like stuff, is that what's more important is actually legacy rather than money, right? Legacy that, I remember one of our collaborators, Professor Hartung from Johns Hopkins, was saying that it's not every day you get to wake up and invent a new field of science. And I was like, you know what? You're right. My team, particularly Brett, and the research team, have invented a new field of science. And it's not every day we get to do it. And so I feel very privileged and very, grateful to be part of this journey. And the greatest outcome for this, I think, is the legacy, right? Being able to say, I made this. A lot of people are using it, and this has changed the world, kind of thing.
That's an interesting way to think about it, for sure.
Reminds me of that sort of the recent OpenAI Dev Day where Sam just got up very casually, was like, so we made this thing and like people are using it. And
he's like, I'm gonna watch this. I'm gonna build a GPT.
Yeah,
whatever.
Yeah, exactly.
Good. So, what do you see in the next 5 years? What do you perceive to happen?
It's a great question. It's very hard to say. It's a chaotic system. So the further out you get, the more random, more stochastic it looks like. But I can say what I would like to see is more of our work, being completed, looking at how we can correlate the disease modeling stuff. So, I've had parents reach out to me with, cases of kids with, microdeletions in their chromosomes, or they've had kids with, lissencephaly and all these things who are like, I don't know if you can help me, but, I would really wish that your system could, be used to find treatments for my kid's condition. A lot of heart-wrenching stories. Carers with parents with dementia who like, it's maybe a bit too late, but I hope that this technology can be used to either A, find a drug, or B, understand better the disease state. So I really hope in the next 5 years we're able to progress that a bit further. There is now momentum in the US with Congress passing the FDA Modernization Act, where we are now starting to look at alternatives to animal testing in the preclinical stage. So this gives us an opportunity to start thinking about, can we start using organoids for this kind of work? And then if that's the case, what are the large scale studies that we have to start thinking about, where we can start doing multi-center trials, and we can get enough data and statistical power to say, look, there is a correlation between what happens in a donor dish and the donor itself. And once we can prove that, I think that's going to change the way we practice medicine significantly.
Is that the most exciting aspect of the future of Cortical Labs to you? Like the
It's the one that we have the most amount of control. The other one that's really exciting that we have really not much control of is the cloud computing aspect of things, where we are building tooling, to program these neurons in JavaScript and Python and putting it out there. So this hopefully will be launched sometime next year. We have no idea what people are going to be building on it or where they'll take it or if it's going to do anything. But it could be really cool. Like, it's like, who knew what people were going to do with ChatGPT when it came out?
Wow. So you're almost building like an Azure, but for biological computing.
Correct.
That's so fascinating. You just got a bunch of like brains instead of GPU clusters. So,
pretty much. So
yeah.
the way it would work is you would say, I'm very keen to do some experimentation. I have some ideas how these things could work. I'm going to adopt the cell culture. So you let us know what type of cells you want. We grow them for you. And then once they're matured within usually about 2 to 6 weeks, we say, okay, it's ready to go. Give us your code. We'll run it for you. And we'll run the experiments and we'll give you the data back. But in the meantime, we're looking after your cells. And, you get something that's really cool, right? So, it's share it around, publish your work, build a startup, who knows?
Do you think that biological computing is a prerequisite for AGI?
I think it is for some types of AGI.
What types of AGI?
The ones that are self-sustaining, i.e., if you think about it, like most of the current systems, unless they feed themselves back, are functions. F of x equals y, right? You don't give it an x, you don't get a y, unless you feed y back to itself. But then you end up with a loop that doesn't really make any sense. Biological systems we don't function like a mathematical function. We're just here. We input, we action. So I think it's quite a prerequisite alongside with embodiment to actually get to this kind of AGI that we're kind of familiar with. That's kind of the reason why some people say that ChatGPT is AGI, but a lot of people disagree because it lacks the embodiment. It lacks the ability to just respond, right? Because you have to prompt it to get a response back.
So you mentioned, you've been to the US many times. Do you see yourself moving there in the future?
Potentially. It's really up to the investors, really. So a lot of the times investors will make a prerequisite for the CEO to be on site, where it's easy for them to get a hold of. And scalability wise, maybe we might need talent that we may not be able to find in Australia. Overseas in the US, the UK, Asia, wherever. So it's hard to say. I'd like to stay here, but you can never tell.
I mean, we didn't even cover this, but the actual facility that you work in, what does that look like? Is it a lab?
Yeah, it's a lab. It's down in Brunswick, actually. So it's a PC2 laboratory. We grow the stem cells there. We plate the neurons, and we keep them alive. So we actually have a set of neurons that have been growing since actually they've been around for much longer than August, but they were capped and put in the perfusion circuit system since August. So we're like August, September, October, November. So 4 months outside of an incubator, outside of a human body, and it's just being perfused with cell culture media using our system. And they're still alive and they're actually doing pretty well. So yeah, that's what a laboratory looks like. Kind of the same that you would get in, university laboratory kind of thing.
Do you feel like though there's a certain scale of ambition that's only possible in places like San Francisco that you can't get in Melbourne? That if you have like really ambitious ideas, you almost have to move to the US or at least pitch to the US? Or, what are your thoughts on that?
I think actually there's an antithesis to that in San Francisco right now. Anything that's too hard gets outright dismissed as fake. It's the Theranos effect. Anyone who's doing anything hard is now looked at as a fraud. And so I don't know if it actually really makes much of a difference if you're in San Francisco or not. In many cases, like Neuralink is actually based in Texas, I think, and Synchron are based in New York. So I'd say that deep tech is actually not focused that much on San Francisco. There's a lot of good deep tech stuff there, but I don't think it's a prerequisite that you have to be in the Bay Area to succeed. In fact, it actually is an equal chance if you're outside as well, because you don't have to fight so hard for talent and compete against big tech.
Right.
Very true.
Shall we move on?
Let's move on.
So we want to have a bit of fun now.
Yep.
Essentially, speed things up a little bit. We go
Uh-huh.
through what's called the quick fire round,
Mhm.
where we ask you a series of questions that were generated by AI.
Okay.
Your task is to just respond
All right.
intuitively to what first thing that comes to mind.
Okay.
So first question, what is your favorite way to chill?
Netflix.
What's your favorite cuisine or restaurant?
Japanese.
If you had to go back 100 years, what would your job be?
The Lord Chamberlain. I wiped the king's ass.
Why?
Because that's how you get the most amount of power and influence. Yes, me lord. Yes. Now, I have this problem, Oh, yes, very well. Okay, no problems then. We'll take care of that. While you wipe it to the ass, the royal ass.
Oh, that's like the most fascinating way anyone could have answered that question. If you had to choose one animal to be your battle companion, which animal would it be?
The honey badger.
Why?
Because it's unbeatable. No fucks given. Oops, not necessarily say that.
That's okay.
What's your favorite snack?
Doritos.
If you had to teach a primary school class on one thing, what would you teach and why?
Coding. I would teach in Python because it's very useful.
Nice. If you could time travel, would you go into the past or the future?
I go back in the past
Why?
so that I can get a lottery. We know Back to the Future disproved it, but I get a lottery ticket.
What would you do with the money?
Don't know.
Cortical Labs.
Yeah, I'd just be a VC and I'd just fund other people.
Yeah, that's right. Maybe one more.
What's one subject you would like to learn more about?
One subject I would love to learn more. Maths. Right. There's always so much and there's not enough that you can learn.
I have a friend of mine that's doing maths and all he does is maths. He lost his girlfriend because he would choose choose maths over his girlfriend.
There's a particular type of character and personality that goes down that path.
Oh man, the math department, so crazy.
But to be honest, like having conversations with mathematicians is quite interesting.
Yes.
Even if you don't understand the concepts, just to see someone, geek out like that.
Yep.
It's a different type of human.
Absolutely. Do we have a question from the last?
I can't remember what the question was.
Let's give you a new question.
An intellectual question.
All right.
What do you think you want your legacy to be?
I would love the legacy to be that I created a startup that gave birth to many other startups. Right. I want to be the anti-OpenAI. I am not going to compete against smaller startups building on our technology. I think they made a mistake with their app strategy, because you have to be invested in it. You need to know how you're going to make it work, and at least for our technology, because it's so new and it's so young, we got to give everyone who builds on our system the best shot possible at succeeding. So yeah, I would really hope that the legacy would be that we get 10 startups, maybe they become not startups anymore in the future. And, we would have a whole bunch of technologies built using what we discovered in our lab, 4 years ago.
I think the brilliance of that is that you're well on your way. It seems, at least.
I hope so.
So awesome job with that.
Thank you.
Having said that, passing on the torch, what is a question that you want to leave on the Orange podcast for the next guest?
I think the question would be, think about what are the applications that could benefit from real time? So operating with sort of data streaming in at a constant, clock speed like what we have right now, that needs low energy. Think about it and then reach out to us when the system is ready, and we would love to see what you can build on top of it.
Brilliant.
Fascinating. Well, this has been the Orange Podcast, gladly sponsored by Melbourne Connect Co-working. Happy to have you on, and thank you for joining us.
Thanks for having me.
Now, we talk a lot about business and entrepreneurship, but to build the future, you need people and a place to build from.
Discover the perfect workspace for collaboration and productivity.
Melbourne Connect Co-working is offering our viewers an exclusive 25% discount on 12-month memberships.
Quote orange when you submit your inquiry. Links are available in the description now.